Hey there, team! Chemistry coach coming at you for a new day in our journey on Introduction to Matter. We're going to do more journeys later on, focusing on each type of matter, but we just got to talk about it in general. So we looked at properties of matter last time and kind of introduced chemistry and whatnot, matter and energy. And again, we'll focus on energy later. Matter is our primary goal at this point. So let's take a look at how we classify matter. Breaking things up. I mean, if you take biology, you take a look, it's like this mushroom or that virus or that bacteria or that cheetah, and you can put them in the kingdoms and phyla. I'm not a biology guy, right? But you put them in these boxes, and biology was many, many decades ago. And I remember there was a lot of boxes you could put those in. I'm like, oh man, it just spread like a Christmas tree. And I'm like, oh, chemists don't like so many boxes, right? We're just going to have a few, right? You can count them easily. I mean, for some people teach it, there's enough boxes you can put them on one hand. I'll add a little more layer of detail to it than what you'll typically read in a textbook, kind of introducing some of what we're going to see later. But I want to introduce some terminology first. When you hear chemists throwing out these, concepts, I want you to have an understanding on a way down. Macroscopic is what you see. They typically say microscopic is what you can't see, although chemists usually like to say down on an atomic level or molecular level. But for all the matter that we're going to deal with in general chemistry, we can really just say all of this matter is going to be made up of particles, right? And we'll talk about the energy that holds those particles together much later down the road. But they're all going to consist of one of three types of fundamental particles, right? We're going to spend a lot of time on atoms. There's going to be a whole journey just on atoms. But I want to introduce that concept because an atom is the smallest fundamental particle that retains a chemical identity, right? It's indivisible. We're going to find out later that consists of subatomic particles. You've heard of electrons, protons, neutrons, but those don't have a chemical identity. When you combine those together in a specific way, you get an atom, the smallest fundamental particle of matter that retains a chemical identity. Like this is an atom of carbon, this is an atom of nitrogen, or this is an atom of tungsten, because the way those subatomic particles we'll learn about later are combined. Let's picture that as a sphere, right? So let's just say an atom, just as a sphere, like a marble or something like that. We can chemically combine atoms together. We'll talk about the forces that make that happen much later down the road. But if you combine two atoms together, or 3 or 5 or 12 or 300, it doesn't matter. As long as it's 2 or more, we get what's called a molecule. So when somebody throws around this concept called a molecule, it's a particle of matter that has a chemical identity. Everybody's familiar with the H2O for water, right? Well, that'd be 3 atoms, 2 of hydrogen, 1 of oxygen. Those atoms can be from the same element or from 2 or more different elements. It doesn't matter. So sugar has carbon, hydrogen, oxygen. So it has atoms of 3 different elements combined in there. So we're going to just draw the atoms as spheres. For example, let's say if we had water, the oxygen has that purple color, and then the hydrogens have the blue color. Right? So you can think of it, put an oxygen here, starting to look like Mickey Mouse quite a bit. Right? So that would consist of one of the fundamental particles of matter. So we got 3 atoms in there from 2 different elements. We could have a molecule, again, like I said, with atoms all from the same element. For example, let's say we have this. Let's say those 2 atoms are combined together, and they're both nitrogen, right? So we have these 2 atoms connected together, so they are technically a molecule. And we'll find out we use formulas with subscripts to tell us how many atoms there are of each element in there. Right? And we'll learn later that's called a diatomic element. Right? We're going to get into classification of matter and the elements and compounds and stuff in a little bit. But I want you to get these terms. I see a lot of beginning chemistry students get confused between what a molecule is versus an atom. Not so much those two, but when I get into compounds later, compounds versus elements, they get the molecules mixed up in there. So again, molecule, Just two or more atoms combined together chemically. Doesn't matter what elements they're from. They can be two different elements or the same. And lastly, we're going to run into compounds and other species made up of charged atoms or charged ions. They're known. So molecules and the atoms are neutral. They have a net zero charge. But we can play around with it. We'll learn about losing and gaining electrons later down the road, right? Giving you a little glimpse into your future. Charged atoms, right? So if that had a positive charge or a negative charge or a positive 3 charge or a negative 4 charge, that would be a monatomic ion. So one atom that's charged. If we take a molecule and make it positive or negative 3 or positive 2 or whatever, that would be a charged molecule. It has many atoms, so we call that polyatomic ions. Oh, the bane to a lot of general chemistry students' existences. So what we're going to do is we're going to do those boxes, and we'll take matter in general and just break them up into different types of categories. And we want to be able to take any form of matter and go, what box would that fit in? Let's go through those boxes. So what you want to do is get a blank piece of paper, twist it sideways so it looks like this board, and we're just going to flow down through all these boxes. So we'll break matter up into like 2 things, and each of those will break up into 2 things. Much easier than biology, though. You ready to fill in some boxes, my friends? Actually, usually all you see is that. So chemistry is way easier to classify. And you think matter, that's like pretty much everything in the universe, right? As long as it has mass and volume. And we just stick it in 1, 2, 3, 4, 5, 6 different boxes. Yeah, it's just less to memorize than biology, right? And I'm going to add 4 more boxes which talk about those fundamental particles that we talked about, ions, atoms, and molecules. So just a little glimpse into the future. Probably a little beyond what you'd usually get this early in the journey. So let's start with matter, right? Could be anything. Could be a penny. Could be a leaf from a tree, your eyeball, some phlegm. Doesn't matter what it is. Matter. We're going to break those into one of 2 different things. Fundamentally, either it's going to be pure, right? Whatever it is, doesn't matter what it is, but it's pure. It's untainted by something else, so a pure substance. Or it will be a mixture of 2 or more pure substances, right? So I can have, sand and water, or I could have a sand-water mixture. Makes sense, right? So let's put a pure substance here. Write that in. Put the pure substance there. And then put the mixture right there. Fundamentally, the most simplest way to break things down. It's either a mixture or a pure substance. And if you just want to define a mixture, it's 2 or more pure substances physically mixed. They're not chemically combined, right? I can mix the sand and the water, right? It's pretty easy to do. I can separate those back out again, and I can mix them in any proportions, right? I could have 10 milliliters of water and, a gram of sand, or 2 grams of sand, or 40 milliliters. It doesn't matter. I can mix them any way I want. It could be, 50%, 50%, 90% one, 10% the other, whatever I want. They're just physically mixed. That key term, remember we talked about physical chemical properties? So this is 2 or more pure substances, whatever they are. And they could be the same pure substance, right? So I could have the same species but 2 different phases. Right? I could have solid water or ice and liquid water together, right? That would be a mixture, right? 2 or more pure substances physically combined. If you want to have a squishy I want to get all of this just on one board here, so I'm going to put little squishy definitions. You can read more details in, textbooks or online or on videos, whatever. But the key word here is physically combined, right? In any proportion, right? If you want to add in any proportion, that's great. All right. Well, let's go. We could start with either one of these. Doesn't really matter. So we have a little more space over here. Let's take these. Now we'll do pure substances because we're going to break those down a little bit. The next video after this, we're going to talk about how to go from like a mixture to its pure substances. How do we do that? Called separate. We're going to separate them. They're called separation techniques. That'll be the next video. All right, well, let's look at our pure substances. That's going to be one of 2 things. Either that is going to be an element, and we're going to spend an entire video on those later, or a compound. Element or a compound. We're going to do a whole journey just on compounds, right? And the whole video just on elements. So let's look at the definitions of these, all right? So think of the element as the basic building block. I didn't leave a lot of room there. And a compound, actually, I'm going to make a little more room to put a definition there. So I'll pull those 4 boxes down a little bit. So let's call this the basic building block. Of all matter, right? And we know those consist of ions. And the compound will be 2 or more elements. So a compound and a mixture are kind of similar, where a mixture is 2 or more pure substances. A compound is 2 or more elements, but these are chemically combined. That's the key right there. Chemically combined. And you'll see when you change the way atoms are arranged in there, you change the chemical and physical properties, which are based on the atomic arrangement. So I can have 2 different elements, for example, sodium, which, I don't have an example with me. It's kind of a soft, silvery, grayish metal. You can cut it with a knife. It's amazingly soft. Explodes in water. You eat it, you die probably, right? Fire-breathing dragon wouldn't be a lot of fun. So sodium by itself is deadly. Chlorine, on the other hand, is also an element. It's a green, kind of a greenish colored toxic gas. You wouldn't want to be breathing it. You're a Dungeons and Dragons person. Green dragon, right? But if I mix those elements together, you'll see an energy change. It's actually a pretty bright light, a little bit of flame. And if I mix those chemically, I form a completely new substance with a new atomic arrangement. I've now got the sodium and the chlorine chemically combined to get table salt, right? So the chemical and physical properties of table salt are completely different than the original elements that you combine. Now, the thing about chemically combining is, we're going to find out when we talk about compounds, those are in set ratios. There's a law about that, the law of constant composition. So we are limited to how those elements combine to form compounds. They go in very specific ratios. Where when you're combining pure substances to form a mixture, you can do it in any ratio you want because they're physically mixed. Keep that in mind. Chemical, physical, chemical, physical. All right. So we can break down, and now usually the textbook won't go further than this, but we can break down these elements into 2 types. Now, all the atoms, they're made up of atoms, the fundamental particles, right? So let's put, let me get the right color. So let's put atoms here. So either that element's just going to be like a box full of marbles, and all those marbles are exactly the same, right? So we would call that a monatomic element. Right? So any element consisting of just individual atoms, like little marbles that are all the same, we're going to call that a monatomic element. But some of these elements consist of particles that are molecules. And a lot of students get confused on that one. So there's 2 different types of elements. There's monatomic elements, where all the atoms are individual particles, or they're made up of atoms combined chemically to form molecules. Most of the ones like this just have 2, right? So there's 2 of them stuck together like a dumbbell, like that nitrogen I showed you earlier. It could be more than 2 atoms, could be 4, like so phosphorus, you might see a P sub 4, right? So it exists as 4 phosphorus atoms combined together. Any combination like that would be a polyatomic one. We're going to just focus on the diatomic ones specifically. But these ones, where's my color here? So we'll call these polyatomic. And there's a list of very common diatomic ones I want you to memorize because they're super. They're some of those representative or main group elements. So let's look at it as an example, i.e. diatomic elements. And there's little catchphrases for remembering this. I've heard somebody say Brinkelhoff. I've heard some things about hot dogs. I mean, it's just however it works for you. But if you look at the periodic table, there's a group of elements that exist in the diatomic state. They exist as diatomic molecules. So hydrogen's one of the main ones. Nitrogen, oxygen, fluorine, and then a lot of these, and the chlorine, bromine, iodine. So it's kind of this, upside down, kind of a reverse number 7 or so. I call it the Magnificent 7. So hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. And whatever catchphrase you use for that is great. Doesn't matter to me. But let me write these down. So hydrogen, nitrogen, oxygen. Right? If you follow this around, there's your hydrogen, your nitrogen, your oxygen. Let's go to the fluorine and then down that way. So we've got fluorine, chlorine, bromine, and iodine. Having trouble squishing the I2 on there. I showed you the iodine in a prior video. It's that one that sublimes in this beautiful purple vapor. I just love it. So I call it the Magnificent 7. Great movie with Yul Brynner. At least not the old one, but kind of the older one, but not the oldest one. I think there's 3 different versions of Magnificent 7. So the one with Yul Brynner, with a knife fighter fighting a gunfighter. Oh, it's just awesome stuff. So you'll get the Brinkelhoff, whatever works for you. But remember those ones. Those are by far the most common polyatomic elements. They all happen to be diatomic. And again, you'll see like a P4, maybe an S8 here and there. But just make the assumption at this point, when we're dealing with elements in my class, these 7 are going to be diatomic and the rest will be monatomic unless otherwise specified. But memorize those babies. Write those down on a flashcard or something like that. Keep it in your pocket. Put it on your phone while you're stuck at a red light, at a boring date, on the toilet, whatever, good in, bad out, whatever works for you, man. I used to think about, I'm like, man, I could laminate notes and put it in the shower. I could study when I'm showering, trying to be as efficient as possible, walking across campus, blah, 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 right? So anyway, that breaks down the elements there, and they can be either monatomic or polyatomic, exist as atoms or molecules. So let's look at compounds here. 2 or more elements chemically combined. So now I'm going to erase this and put 2 boxes here. And compounds can exist as one of those 2 fundamental particles, right? They couldn't consist of atoms, right? Because a compound's 2 or more elements chemically combined. So you have to have at least 2 atoms of 2 different elements. So a compound could not exist as atoms, as fundamental particles. But I could have a compound consisting of molecules, all right? Just like I can have elements. And this is where some students get confused. This is why I add this in here. It's not typically added in there. So a molecule is not necessarily always a compound. It could also be part of an element. Could be one of these diatomic elements, right? But it could be also water or carbon dioxide, CO2 or sugars, glucose, things like that. So compounds can be molecules, or we're going to see many compounds consist of ions, and we're going to spend a lot of time on both of these. So we have molecular compounds and ionic compounds. So like your sodium chloride, stuff like that. That's your typical ionic compound, whereas water, carbon dioxide are your typical molecules here. So if you want to put some examples in there, right? So we could put H2O, CO2. This could be NaCl. Probably the most famous ones right there. And we'll talk about what makes molecular compounds different than ionic compounds. Just some extra stuff there. Got a little squishy, but I just want to throw that at you. Let's take a look at mixtures here. 2 or more pure substances. So that would be elements or compounds, right? So I could have 2 or more elements physically combined, not chemically reacting. Because not all elements are going to chemically react when you stick them together, right? I could take, a chunk of iron and a chunk of manganese and throw them in a box together. Nothing's going to happen, right? I could take, powdered steel and mix it with powder. Well, steel's not really an element, but that's a compound. I could mix any 2 things, whether it's 2 or more compounds, 2 or more elements with compounds, as long as they don't chemically react with each other. I can physically mix them in any proportion I want, boop, and get myself a mixture. What designates the 2 different kinds of mixtures is how they mix, All right. Do they mix evenly throughout? So when you look at it, you can't tell visibly that it's actually two different pure substances. It looks like one thing. Or are they not mixed evenly? And you can see macroscopically with your eyeballs, I can see two different things. I can see that sand floating on the bottom, floating on the bottom. What does that even mean? Sitting on the bottom of a beaker, like if I put water in this beaker and some sand, the sand would sink to the bottom. And I can see the sand and I can see the water. But if I put salt in the water, the salt dissolves and spreads out and it just looks like pure water. Okay, so you get salt water. So that gives us two different kinds of mixtures, right? And we use the prefixes. Homo means same, hetero means different. So if it looks the same throughout, it looks like one substance because they mix so evenly, we call that a homogeneous mixture. Some people say homogeneous. And if they don't, if it's not mixed evenly, and you can definitely see two or more pure substances in there, we call that a heterogeneous mixture. So this will be homogeneous. And this will be hetero. So pretty easy. Now, what I had the most trouble with was homogeneous mixtures versus compounds, right? Turns out because compounds have a set specific ratio. They only mix in one specific ratio, like H2O, CO2, NaCl, 1 to 1, 2 to 1, 2 to 1, right? But physically, mixing, you can put them in any proportion. So homogeneous mixtures do not have chemical formulas with specific subscripts. The subscripts tell you the specific ratio. So whenever you see subscripts like this, boom, that's got to be a compound, right? As long as it's got two or more elements in it. But you will never see a formula or subscripts for a mixture, right? So homogeneous means the same throughout. So it looks, if you want to put it in there, looks like one substance. It looks pure. So heterogeneous is not evenly mixed. So heterogeneous mixture is not evenly mixed, and you can see two or more phases. Or not really phases, but two or more pure substances. So whatever those pure substances are, you can see them. Like I said, like the ice cube over liquid water. Those are the same pure substance, but they can be two different things, the sand and the water or whatever. So great example for this, like I said, is salt water. And this would be like sand in water. Very easy. You know, a banana split. I can see the ice cream. I can see if there's a cherry on top. I can see the cherry stem. You're a walking heterogeneous mixture, right? You got fluid. I can see my nose, my eyeball. If I cut myself, I can see some blood, right? But homogeneous mixtures look the same. And again, just looking at it, you wouldn't be able to tell the difference between a homogeneous mixture and a compound. You would need more information, right? So if you take, you get a bottle of Gatorade or something like that, it looks like a pure substance, but you look on the ingredients, I see sugar, maybe a dye, water, those kinds of things. So that's definitely would be a homogeneous type mixture. Soda pop is a confusing one because it depends, can you see the bubbles in there, right? So like flat soda pop, right? You don't see any bubbles. It's got the sugar, yellow dye number 5 for the fellow doers out there, right? Caffeine, water. There's definitely two or more substances in there. And if it looks the same throughout, we call that homogeneous. But if I open up soda pop and I can see the bubbles, I can see those are carbon dioxide bubbles. I can see the two different substances. That would make it heterogeneous. So sometimes it gets confusing if there's not enough detail provided, right? Somebody says air. Well, I would think air would be homogeneous because I know there's nitrogen in it, there's oxygen in it. If you have a bad burrito, there might be some hydrogen sulfide in there. Maybe, ozone floating around. But if there had been a recent fire and you see particles of smoke, I can see the little solid particles of smoke floating in the air. Well, that would make it heterogeneous. Just like ocean water. Well, it's technically salt water, so it looks homogeneous. But sometimes when I go in the ocean, I'm a Southern California guy, I see little particles of like gold flakes or maybe some seaweed, chunk of feces from some kid down there. No, I'm just kidding. Right? That would make it heterogeneous. So realize sometimes you need more information. Orange juice is one that got me, right? I was like, orange juice. I immediately said heterogeneous. Because when I drank orange juice growing up, it had the pulp. I hate the pulp. It's like, ugh, I get little pieces of pulp in there. But there's also orange juice that's pulp-free, which would be homogeneous. See the difference there? So you would have to specify, wine. Wine is definitely, you got alcohol, you've got water, whatever. I'm not a wine guy, but that's homogeneous. But a fly goes, bloop, and gets in, oh, now it's heterogeneous. There's a fly in my one. That happened to me once I was drinking an energy drink. Flies, you're sitting there watching TV or whatever, and you can see flies in squares or something. They're just irritating. Then you go to get the fly swatter and they disappear. You put the fly swatter away, they come back. I don't get it, right? So I can hear this fly buzzing around, bouncing off the window. I'm like, so irritating. I had this little energy drink with a small little hole, and I nurse my liquids throughout the day. I'm not a chugger. And, about 5 minutes later, I don't hear the fly anymore. And I'm like, that's weird. And so I go to drink the energy drink, and the fly comes in, and it got down in that. What are the odds statistically of the fly going in that little tiny hole? And I'm like, oh, that was such those are like $2 or $3. I'm like, okay, I'm gonna finish it because I'm frugal that way, or I grew up very frugal. I'm not dumping that thing down the sink. It didn't kill me. Kind of gross, but it didn't kill me. But that fly moved in your mouth. So I have a lot of fun with heterogeneous mixtures. That's probably my favorite right there. But again, I just want to warn you, it can be a little confusing sometimes. So what we're going to do on the next video is talk about how do we get from mixtures to pure substances, because those are physically combined. So we're going to need a physical separation technique. And if we want to get from compounds to elements, if we want to break down a compound into its individual elemental components, well, those are chemically combined, so I'm going to need a chemical separation technique. That's a whole video in itself, and I won't be in a lab. We'll talk about the techniques in other lab videos, but we'll just theoretically talk about what are some of the ways we can separate things to one another. But just remember, physically mixed for mixtures, chemically mixed for compounds. That's the key. And be careful with homogeneous mixtures versus compounds. Look for the subscripts. If you see them, you know it's a compound, as long as there's 2 different elements in there. If you don't see them, then you got to go, maybe some practical experience, maybe some ingredients that are on there. You need some more information to help you out, because salt water looks like pure water. You need some more information. All right? So play around with it. Just takes a lot of practice.